Hey guys, this is going to be lesson number 8 for abstract algebra. Today we're going to be learning about p-groups, the p-group fixed point theorem, and Cauchy's theorem. So p-groups are just basically a kind of group whose size is the power of a prime number. So let's define that real quick. Define a group G is a p-group if the order of G equals p to the n for a prime p and n is some natural number. And the definition also includes the trivial group to be a p group, but usually we don't think about it too much because it's not really helpful for our theorems. Okay. So the question is, why is this definition helpful? So try to think of why might this definition give us some helpful results? Well, if we remember Lagrange's theorem, it tells us that the size of a subgroup in G, let's assume G is a p group, then the size of G, the size of the order of H as a subgroup has to divide the order of the group. That's at least a result from Lagrange's theorem. Which means if the order of G equals p to the n, then the only divisors of p to the n are the numbers 1, p squared, all the way to p to the n, of course. So this implies that H itself is also a p group. So the order of H equals p to the m for some smaller m less than or equal to n. I guess H could be the trivial group, and then you would get G mod H is still G. Either way, the size of H is still a p group. So if you can derive results about groups, you also get stuff about their subgroups as well, and you can use this fact, the fact that the size of any subgroup is also a p group or is divisible by p, to derive some nice results. So let's just do a quick corollary here from this definition. If G is a p group and H is a subgroup of G, then H is a p group. We also get if H is normal in G, then we also get that the group G mod H, now note since H is normal, this is a group, G mod H is also a p group. A p group. So that's just something nice to keep in mind, that if you take any subgroup of a p group, you know it's also a p group. Same with quotient groups. Okay, since we've been talking a lot about group actions to prove different theorems in the lesson so far, one might ask, what happens when G as a p group acts on a set X? When G acts on a set X. Okay, well, let's see. We know that we can take orbits of X, orbits of elements, and we can describe the size of these orbits. So let's say take some X and X. We know from the orbit stabilizer theorem that the size of the orbit is the size of G divided by the size of the stabilizer of that element. But remember that the stabilizer is a subgroup of G, which means that this has to equal some p to the m. So we basically get that the size of any orbit is also p to the m for some m, because the stabilizer is a p group, G is a p group, so dividing them is just going to get you another power of p. But we do have a special case, which is, in general, we're going to get that p divides the order of any orbit for any x, except when we get that the stabilizer of x equals, or should I say the order of the stabilizer equals the order of the group, which implies that the stabilizer of X equals the group. And in this case, we get that the order of the element is just, or the order of the orbit is just 1, because G divided by the stabilizer is just 1 if they're the same. So we get, in every case, P divides the size of orbits, except for when the stabilizer is the entire group. And this idea of the stabilizer being the entire group is an important enough idea that we have given it its own definition. And it's going to be something called the fixed points of a set. So let's let G act on a set X. Now G is not necessarily a P group anymore. It can be any group. The set of fixed points which I'm going to denote, or should I say of X, is denoted X to the G. Don't think of this like an exponentiation anyway, it's just a weird notation, but it's kind of fun to write. Equals those elements in X such that G dot X equals X for all G in G. You can also think of this as those elements X and X such that the stabilizer of X equals the entire group. Because that's just the definition of the stabilizer. The stabilizer is all those elements that fix X. So if everything fixes X, then the stabilizer is everything. Now that we have this definition, we can kind of notice something, which is, like I said, when we're kind of like thinking about the X here, we can either think of it in terms of the orbits of X. So you have a bunch of orbits, O of x2, let's say to O of xk, that kind of partition X. But some of these are going to be divisible by P, and some of them are just going to be equal to 1. And so an interesting idea, if I want to learn more about these fixed points, is to consider what is the size of my set mod P. Because if I can group a lot of elements into sizes of order something divisible by P, I might get them to cancel out, and it might tell me something about the fixed points of this set, because the fixed points are not divisible by P. Or at least the orbit of any fixed point is just size 1. Okay, and this is going to lead us to the P group fixed point theorem, or sometimes called the P group fixed point lemma, but I'm going to write it as a theorem here. P group fixed point theorem, which says let G be a P group and G acts on a set X. Then we get the order of the fixed points of X are equivalent to the order of X mod P. So that's kind of the exact idea I was describing up here. We can take the set mod P and see if we can relate it to the size of the fixed points, which is exactly what this theorem tells us. So let's prove it. Okay. So we're going to split up X into a clever way. We can write X equals the set of fixed points union, well, the set of non-fixed points, which is, this is a pretty obvious statement. This is, of course, true. I can write it as the set of something union all the other things, and that's the entire set. Now what I'm going to do is I'm going to take this X minus xg, all the non-fixed points, and I'm going to partition them into orbits. So choose points x1 through xk in X minus xg such that X minus xg is going to equal OX1, so the orbit of x1, union the orbit of x2, union all the way to the orbit of xk. So I'm basically choosing some elements, taking their orbits, and rewriting x minus xg as the union of those orbits. Of course, remember that all these orbits are disjoint from each other. And so now I can write x, my entire set, as xg union all these orbits. x1 union ox2 union all the way to union oxk. Okay. But we know, like I said, that all of these are disjoint. And so what I want to prove is I want to rewrite this, I want to rewrite the order of x to be the sum of the orders of all of these. But before I do that, I have to know that all the sets are disjoint, because if they're not, then there might be some overlap and my sum is wrong. So I know that all of these are disjoint. Now I need to prove that xg is disjoint with all of them. Okay, well, let's assume, by way of contradiction, that xg intersect O of xi for some I doesn't equal the empty set, and that there's some element that's similar between the two. So this implies there exists x and O of xi such that, well, the stabilizer of x equals g, because that's just the definition of the fixed points. But we know that, I can now consider the orbit of x. We know that the orbit of x has to equal the orbit of xi, just by definition. That's how orbits work. If they have any intersection, they have to be equal to each other. They're either disjoint or equal. And so these orbits both have x in them, so they have to be equal. But the orbit of O of x equals 1. Because, like we said, the orbit is just g divided by the order of g divided by the order of the stabilizer, which is 1. But if the size of the O of x is 1, then the size of O of xi is 1, which would then imply that xi equals x, which is a contradiction, because we assumed that xi was not a fixed point, because xi not in xg. Okay, so we know that xg has to also be disjoint from all of these guys as well. So I can finally write the size of x equals the size of the fixed points plus a sum of the size of all the orbits. Let's say from I equals 1 to k of O of xi. So finally we see that from above we get that p divides the size of the orbits of O of xi, because they're not fixed points. So if I take both sides mod p, I get that x mod p is going to be congruent to just xg, because all of these go to 0 mod p. And then we just get our theorem exactly how we wanted it. Okay. So you might be asking, okay, like why the hell would I want this? I mean, what is this really helpful for? Well, the reason why it might be helpful is because you could come up with a clever set x and a clever group action, and you can prove certain things are non-zero. For example, if I had, like, let's say my set was divisible by p or something, then I could get that, like, xg was 0 mod p. Or other way around, if I knew the fixed points were, divisible by p. And then, let's say I knew there was some element, like I knew that xg didn't equal 0. Then I know it has to be at least p, or 2p, or 3p, so on and so forth. So you can prove that there's a lot of more elements in certain sets than one might think at first. Because, of course, if you know there's none of them, it could easily be 0. But if you know there's at least one of them, then there has to be at least p. And it could be any multiple of p even. So what we're going to try to do is we're going to try to come up with clever sets and clever group actions to prove general theorems about groups now. So, okay, first one is pretty easy, which is a basic corollary. If p doesn't divide, that means doesn't divide the order of x, Well, then we get the order of xg has to be greater than 0, or there is some fixed point. I mean, the proof of this is pretty easy. We know that, of course, this is implying that a p group is acting on x. This implies that the order of x mod p is equivalent to order of xg, but the order of x mod p is non-zero because p doesn't divide order of x. So this is just sum a xg mod p. So the size of xg equals like n times p plus a, which is of course non-zero. Okay, so that's just something to note. If the size of my set is not divisible by p, I must have a fixed point somewhere. That's a pretty basic result. Now let's get a more interesting result. And this has to do with the center of a group, or a p group I should say. And remember, the center is all those elements that commute with all other elements in the group. This is an important idea because centers allow us to kind of extract abelian subgroups from bigger groups. If G is a p group, then Z of G is non-trivial. So it's just like not just equal to 1. Of course, 1 is in the center. It always is because 1 commutes with everything. But this theorem is saying if G is a p group, then there's got to be more stuff than just 1. Okay, let's prove this. So for this, we're going to consider G acting on itself. This allows us to apply the p group fixed point lemma because you have a p group acting on a set, which we're considering G as the set here, by G dot H equals G H G inverse. And if you remember, this is the conjugation action. So we know, first of all, the fixed points, the size of the fixed points are equivalent to 0 mod p because, well, our set is G and G is divisible by p because it's a p group. Okay. So this is kind of the setup we just showed before, where you have something is 0 mod p. If we can show there's something already in there, we can show there's a lot of stuff in there. Let's first describe what the fixed points are. So we see that the fixed points are all those elements h and g such that g h g inverse equals h for all g and g. But if I multiply on the right by g, canceling out this g inverse, this implies that gh equals hg. But this is the exact definition of the center. It's those elements h that commute with everything in G. Thus, the fixed points of G under this group action is equal to the center. Okay, now we're getting somewhere. Now we have the order of the center of G is congruent to 0 mod p. Now remember what I said before, is this could just imply that the order of the center is 0. That's not helpful. But we know that there's something in the center. 1 is always in the center. So the order of Z of G doesn't equal 0. And this implies, from the fact that it has to be 0 mod p, this implies the order of Z of G must be greater than or equal to p. So it implies that it's non-trivial. In fact, we know that the order has to divide p, which is also interesting. But that was evident from the fact that G was a p group as well. So now you've gotten like a taste of what this theorem can prove for us, the p group fixed point theorem. We're going to prove an even cooler result now, which is called Cauchy's theorem. Before we do the proof, I'm going to introduce the statement, and then we're going to kind of build some intuition for how we're going to prove it. Because the way I'm going to prove it is a cool way of doing it. It's using the p group fixed point theorem, but it's not necessarily the most intuitive approach, unless you kind of build up the reasoning. Okay. So let G be any group, so not a P group right now, be a group. If P, some prime P, divides the order of G, so let's say, G is order 20, I could consider P is 5 or P is 2, then there exists an element G in G such that the order of G equals P. So this is a really powerful theorem, and it's going to build up to, it's kind of a special case of the CELO theorems, if you've heard of those, which we're going to prove soon. You could kind of think of this in a way, it's clawing back that converse Lagrange's theorem, which asked us if the order of H or of like n divides the order of a group, is there a subgroup of order n? And this tells us yes, if n is a prime. So if there's a prime that divides the order of the group, there is a subgroup of order p. And it's in fact that group that's 1g, g squared, up to g to the p minus 1, because there's this element of order p. So it's kind of guaranteeing us, if you have some group, I can at least tell you something about the elements in there. I can tell you something about the order of elements just based on what the number that group size of that group is. Okay, so let's build the intuition. So we need a P group and a set. And a set. If you remember, the P group doesn't do too much for telling us about like getting results, because really all that matters is the action that the P group has and the fact that it's divisible by P. What matters more is the set. So we need the set to tell us something about elements that could be of order P. So our set should be related to elements of order P. Elements of order P. At least vaguely. So this is what we're going to try. It's not easy guess, but it is interesting. Let's try X equals these elements G1, G2, GP in G to the P. So this is like choosing P different group elements in our group G, such that G1 times G2 all the way times G to the P equals the identity. Okay, so hopefully you can see why this might be somewhat related to elements of order P, because if we can find that there's an element that looks like this, so let me write it out. Notice, if we can find elements that look like this, elements like G, G, G all the way in X, then we get that G to the P equals 1, which implies that G is of order P. Because, of course, remember, if P is a prime, there's nothing smaller that can divide it. So if G to the P equals 1, we kind of know that G has to be order P. Okay. So we want to try to extract elements that look like this. To do that, we want to define a group action that will allow us to find these as fixed points. They're going to try to arise as fixed points of the set and the group action. So we need a P group. There's not too many options, to be fair, just arbitrary P groups. So we're going to try one that we always know exists, which is Z mod P. Okay. What is Z mod P going to do? Well, we have P elements, and if you remember when we were talking about the dihedral group, there was let's say D3, there was a Z mod 3 in D3, which is just the rotations of a triangle. It's kind of like taking the vertices and rotating them one by one, moving them all to one side. You can also think of this as the permutation in the permutation group that moves 1 to 2, 2 to 3, 3 to 4, and then like maybe 4 back to 1. So we're going to apply that idea here. It's just going to try to rotate the elements. So we're going to have that Z mod P acts on our set X by the following action, where 1 dotted with any element equals, well, GP is going to go to the front, and then G1 is going to go here, all the way to GP minus 1. So I basically rotated everything to the right once. This means 2, which is the same as doing 1 and then 1 again, of G1 through GP, is going to look like GP minus 1, GP, G1, then G2, and so on and so forth to GP minus 2. Okay. You understand this. I'm basically rotating everything by the right. So this goes on, so on and so forth. Now we need to describe, now we want to describe the fixed points. Okay. Well, we know if like, let's say, if G1 through GP is in the fixed points, well, we automatically get that 1 dotted with it has to equal G1 through GP. That's just by definition. If you're in a fixed point, everything has to fix it. So let's just choose 1, which generates the whole group. You can prove that if 1 fixes it, then everything fixes it. Okay. Well, we know that 1 dotted with this equals GP, comma G1, comma all the way to GP minus 1 equals G1 all the way to GP. So if I start equating the elements, I get that GP over here has to equal G1. But G1 over here has to equal G2. And G2 over here has to equal G3. I can do this so on and so forth until I get that all the elements are equal to each other. Which means I can just write this as the fixed points are all those elements where everything is equal to each other, such that G to the P equals 1. And of course this is just equivalent to those elements G and G, such that G to the P equals 1. Okay, so now we've fully described our fixed points. It's all those elements of order P, which is exactly what we wanted. Okay, so let's bring it back to the P group fixed point theorem. So we're ready to prove it now. Let's let Z mod P act on X as above. Everything is defined exactly the same. We get that the size of X, the fixed points, is equivalent to the size of X mod P. But let's try to describe what the size of X is. We see that the size of X is actually the size of G to the P minus 1. And let me prove that to you. We get that for like any element G1 through GP in X, we get that G1 times GP equals 1. But you can actually just solve for GP here. We get that GP is just that element that multiplies by GP minus 1 inverse to cancel out with that one, times GP minus 2 inverse, times all the way to G1 inverse. So GP is just totally determined by G1 through GP minus 1, which means you can just take any G1 through GP minus 1 and then get a GP that works, always. Which that just means that the size of x is just the size of g to the p minus 1, because it's all p minus 1 tuples of elements of g. Okay. Thus, since p divides g, we get that p divides x, the order of x. P divides the order of g, then p divides the order of x. So, the size of the fixed points of x is congruent to 0 mod p. But we know that the fixed points are just those elements of order p. And we know there is actually at least one of them. In fact, we know that 1 is in x to z mod p. Because we know that, of course, 1 to the p equals 1. So 1 has to be in x to the z mod p. Thus, the order of x to the z mod p, or the fixed points, is greater than 0. And since it's 0 mod p, we get that it has to be non-trivial. So we've just basically proven that there exists g and g, where g is not equal to 1, such that g to the p equals 1. So there exists an element of order p. Order g equals p, which is exactly what we wanted all along. Okay, so now we're going to end off with some exercises that should hopefully get you some good practice with using p groups and the fixed point theorem and Cauchy's theorem. Okay. Exercises. First one is prove that if G is abelian, and the size of G equals P times Q for distinct primes P and Q, then we get that then G is cyclic. So for this one, think about trying to use Cauchy's theorem. And you might come up to that realization because we have two different primes, and we know Cauchy's theorem tells us a lot about prime numbers and how it relates to group elements. Okay. Exercise 2. This is a more general kind of thing. Prove that every group of order p or p squared is abelian. The case for p is relatively straightforward. We've already done that actually, but p squared is a little bit harder. So take some time to think through that one. In general, it's a pretty helpful thing to know. If you ever encounter a group that's order 9, order 25, you know that it's instantly abelian. Okay. 3, and this one's pretty hard, is going to be prove Fermat's, not last theorem, but Fermat's little theorem, which states that n to the p is congruent to n mod p. And you might have seen if n is not, if n doesn't divide p, or should I say p doesn't divide n, then you get something that's like a to the p is p minus 1 is congruent to 1 mod p, which is very similar. It's the same as multiplying by a on both sides if they are relatively prime. Okay. And just for a hint for this one, also I should say that this was this problem was on a p set that Sam Raskin gave when I took abstract algebra with him. So just to give a hint, which he gave on the p set, which is consider a set Y with size n. So it has n elements. And consider a p group Z mod p acting on a Y to the p. So every group of p elements of Y by rotation, similar to the proof we had where y1 through yp gets sent to, or I should say 1 dot y1 through yp gets sent to yp, y1 through yp minus 1. And hopefully with this hint, you should be able to use the p-group fixed point lemma to prove Fermat's little theorem. Okay, I hope those exercises are helpful. Thanks for watching.